In your project of ERP integration, what queue did you use? You said you have used asynchronous processing so that the month end request spike could be handled. So please tell me more about the queue that you used. You could answer in the lines of, we use Celery with Redis as the broker for most async work and AWS SQS for the integration specific queues that needed durability guarantees and dead letter support out of the box. The split was deliberate. Celery plus Redis handled internal async tasks like cache warming and report generation, where occasional message loss was accepted. SQS handled anything crossing the integration boundary, outbound ERP syncs, webhook fanout, retry queues because we needed at least once delivery, visibility timeouts, and a managed dead letter queue without operating it ourselves. We considered RabbitMQ but didn't want to run another stateful service. When SQS gave us what we needed managed, we considered Kafka, but the throughput was way below where Kafka starts to make sense. We were at thousands per hour, not millions per second. Can you explain back off? We used exponential backoff with full jitter. The base delay was 1 second, maximum 5 minutes, with up to 8 retry attempts before the message went to the dead letter queue that is managed by the stateless AWS SQS. The formula was roughly sleep equal to random of 0 comma minimum of cap comma base into 2 power attempt. Full jitter rather than equal jitter because it spreads load best when many workers retry simultaneously after a downstream outage. Why jitter matters? Without it, when an ERP recovers from a brief outage, every retrying worker hammers it at the same instant. The thundering herd problem, and you knock it over again. Jitter spreads them across the window. Retry classification. Not everything got retried. We had an error taxonomy 4xx for client errors, validation, auth failed fast, and went to DLQ for human review. 429 is rate limit responses honored the retry after header. 5xx and network timeouts got the exponential back off treatment. Item potency keys. Every retry carried the same item potency key, so the ERP didn't double post the same invoice. What were the columns in the audit log table? Here's a defensible schema. The audit log table had roughly these columns. First is ID, which is UUID primary key. Tenant ID for multi-tenants isolation indexed. Entity type, which is including purchase order, invoice, vendor. Entity ID, the internal record ID. External ID, the ID in the target ERP after sync. Then there is operation, which could be create, update, delete, sync. Direction, inbound or outbound. Target system, QuickBooks, NetSuite, etc. Maybe SAP HANA, or maybe Oracle Fusion Cloud, Oracle ERP Cloud. Status pending, success, failed, retrying, DLQ. Attempt count for retry tracking. Request underscore payload, JSON binary, the outbound payload. Response payload, JSON B, what came back. Error code and error message for failures. Correlation ID to trace across services. Created it, completed it for latency analysis. Actor user ID who triggered it, nullable for system initiated. Composite indexes I would mention is tenant ID comma created at desk for tenant audit queries, tenant ID and status for retry sweeps, correlation ID for tracing. Tell me more about the audit log table. The audit log table serves three jobs: compliance, finance customers need a defensible trail of every sync attempt for SOX style audits. Debugging. When a customer says my invoice didn't show up in NetSuite, we need the request payload, the response, the timestamps, and the correlation ID to trace it across services and operational analytics. We build dashboards on top of it for sync success rates, P95 latencies per ERP, and error code distribution. So, mainly three jobs: one is compliance, another is debugging, and another is operational analytics. It was the highest write table in the system. Every sync attempt produced at least one row, sometimes more if we logged intermediate state transitions. It was also the largest by storage because of the JSON binary payloads. We made deliberate trade offs to keep it healthy. We wrote to it asynchronously where possible so audit writes never blocked the sync path. We used JSON-B and not JSON so we could index specific fields, and we partitioned by month once it crossed a few 100 million rows. If the table is few 100 million rows every month, then why not delete the audit log? So you could answer in the lines of two reasons: regulatory and practical. Regulatory, our customers were finance teams running procured to pay for organizations that had retention obligations, SOX, internal audit requirements, vendor dispute windows. These typically demand 7 years of retention for financial transaction records. Deleting an audit row could put a customer out of compliance. Now, practical: when a vendor disputes a payment 6 months later, the audit log is the source of truth that proves we sent the right data to the ERP at the right time. Deleting it means losing the ability to defend the customer. What we did was tier the storage. Recent data, last 90 days, stayed in the hot Postgres table for fast queries. Older data was moved to partition tables, and the oldest partitions were detached and archived to S3 in Parquet format with Athena on top for the rare audit query. Same data, much cheaper, still queryable. How many records were there in the audit log? The hot table last 90 days, which is what we kept in active Postgres, sat at around 8 to 12 million records at steady state across all retained partitions, including archived. It was on the order of 150 to 200 million records by the time I was deep in the project. That's why partitioning and the S3 cold tier mattered. Without that, query performance on the audit dashboards would have degraded fast. And also remember that the deep old data was archived to S3 Glacier Deep Archive, which could also be queried using Athena, but the retrieval times were larger because it is S3 Glacier. What cache did you use for the latency improvement? Redis, deployed as AWS Elastic Cache for Redis in cluster mode with a primary and read replica per shard. We use the cache aside pattern, read through with explicit invalidation on write, not write through, because write through would have coupled cache held to write availability, and we wanted writes to succeed even if cache was degraded. Where did the cache leave? Which layer, which component? This is where you want to see if you actually understand the architecture. So you could say there are three caching layers, each at a different tier. Okay. First is application layer cache, which is Redis cache aside, sat between the fast API service and Postgres. This is where most of the win came from. We cached reference data, vendor lists, GL account mapping, tax codes, approval policy configs. These change infrequently but get read on every sync. TTL of 1 hour with explicit invalidation when admin users edited them. Next is ERP connector metadata, OAuth tokens, rate limit headroom, schema mapping configs per tenant, TTL of 5 minutes. Computed lookups like does this PO already exist in the target ERP for this item potency key, which used to be a Postgres query and became a Redis get. Now, another layer cache is HTTP layer cache. Another layer cache is in process cache. So I am talking about three cache layers: application layer cache, HTTP layer cache, and in process cache. Application layer cache is Redis, and I have already talked about this. It is sitting between fast API service and Postgres. Now HTTP layer cache is for the public REST API. We used cache dash control headers and e tags on read endpoints, so clients with conditional requests got 304 not modified and skipped the body entirely. In process cache, functools.lru cache for things that were truly static within a request lifecycle, like parsed schema definitions and compiled JSON schema validators. This avoided even a Redis round trip for hot paths. Cache invalidation was the hard part. We used a publish on write pattern. When a record was updated in Postgres, the service published an invalidation message that the Redis client subscribed to and used to drop the relevant keys. Was this integration system on-prem or cloud? Fully cloud on AWS. Customers were SaaS hosted single region US East 1 with cross AZHA multi-tenant data isolation at the application layer with tenant ID enforcement on every query and tenant level Postgres row security level as a defense in depth. We had a separate virtual private connect VPC for the production environment with all integration egress going through a NAT gateway. So partner ERP saw a stable set of source IPs we could whitelist. Now, if they ask why not on-prem, mid-market finance customers expected SaaS. On-prem would have meant operating the infrastructure which does not fit our delivery model. The compliance work, SOC2 encrypted at rest with KMS, customer managed keys for the bigger accounts. Let us serve regulated customers without going on-prem. Now, please explain tech stack and components for the integration layer. Okay, so let me give you a clear picture layer by layer. So let's think about the diagram, and head needs to be sharp. First of all, um, yeah, we have multiple layers. Okay, so the first layer that I want to talk about, I'll talk in later details, but the first layer is edge or API layer that is exposed to the customers. Then comes the application layer. Then comes the async or messaging layer. Fourth is integration framework. Fifth is data layer. Sixth is observability layer. Seventh is CI/CD infra layer. Eighth is security layer. Okay. Now let's talk about the edge or API layer. So in this we have AWS application load balancer, AWS WAF, API gateway for public webhook receivers, fast API services behind application load balancer for internal and partner facing APIs, MTLS on partner to partner connections where required. This finishes the edge or API layer. Next is application layer. We have fast API or Python 3.11 async for new services and REST APIs. Django for the legacy admin and customer portal. We did not rewrite working code. Pydantic v2 for request, response validation and open API generation. HTTPX with shared connection pools for outbound ERP calls. Now let's talk about the async or messaging layer. Celery plus Redis for internal async tasks. AWS SQS standard queues for integration work. SQS FIFO where ordering mattered. SNS for fan out one event into multiple downstream queues. Dead letter queues or DLQs on every SQS queue with CloudWatch alarms on death. Integration framework, the connective tissue, a connector abstract base class with concrete implementation for QuickBooks connector, NetSuite connector, Business Central connector, Common concerns lived in the base, retry, idempotency, OAuth refresh, rate limit accounting, telemetry, schema mapping layer, declarative YAML mappings from Procurify's canonical model to each ERP's native schema. Next comes the data layer. The data layer will have database, so Postgres, RDS multi availability zone, main operational store, partition audit log, Redis as elastic cache in cluster mode, cache plus celery broker. Now S3 for cold audit storage in Parquet, maybe in S3 Glacier, raw webhook payloads for replay, and Athena for ad hoc queries on the cold tier. Observability, OpenTelemetry SDK in every service, AWS X-Ray for traces, CloudWatch for metrics and logs, structured JSON logs with correlation IDs, Grafana dashboards on top for sync success rates, P95 latencies per ERP DLQ depth, PagerDuty integration for SLO breaches, CI/CD infra, Circle CI for build, test, deploy, matches Procurify stock, Terraform for infrastructure as code, Docker containers running on ECS Fargate. We considered EKS but did not need Kubernetes complexity for this workload size. GitHub for source, Bitbucket for the legacy repos that hadn't migrated. And on terms of security, AWS secret managers for ERP credentials per tenant, KMS for encryption at rest, IAM roles with least privilege per service, no long lived keys.